Okay, it's already 6 now. We'll wait for a couple of minutes to let other people get opportunity to join. Till then, let me give an introduction. I hope all of you have registered for this course Heat Transfer on NPTEL with course code NOC24-ch17. This is the Heat Transfer course offered by NPTEL, and uh, the first week is over for this course, and today will be the problem solving session for this week's contents. My name is Nidish V. I would be the teaching assistant for you today, and I'm a PhD scholar at IIT Bombay. We see that we have around 3 people other than me have already joined. So I just want to know what is your current level of understanding about heat transfer. Have you already taken this course before, or are you new to this course? Since we are only 3 people joined, we can make this very interactive session. Give me a moment. Yeah, how many of you are attending this heat transfer course for the first time?
First time, sir.
Okay, okay, thank you.
I also first time, sir.
Okay, okay, thank you. So I think, yeah, most of you are attending it for the first time, and I hope you have gone through the lecture, uh, first 5 lecture videos. Those were supposed to cover this week's contents.
Yes, sir.
Yeah.
Done, sir.
Um, these you're able to see my screen, right? My presentation.
Yes, sir.
Can someone? Okay, okay. So these are the week one topics. We had 5 lectures. People are joining. Let me admit them. Okay. We had 5 lectures for these topics. Lecture 1 was a basic introduction to the topic to heat transfer, and lecture 2 involved an introduction to conduction. Lecture 3 talked about energy balance, and can you mute yourself? Okay. And lecture 4 talked about one-dimensional steady-state conduction, introducing the resistance concept. And the last lecture in this week, that is lecture 5, talked about resistances in composite wall cases. All these 5 lectures were like pretty short, I think less than half an hour, and I hope you all have gone through it. So to just jog your memory, I will just list down what were the different contents that we covered in each of these lectures. After that, we'll move on to some problem solving sessions. Okay. In the first lecture, introduction, professor talked about some basic definitions, talking about what is heat transfer and what drives these heat transfer processes, and what are the different causes of this driving forces for these heat transfer processes. Not only heat transfer, the professor talked about mass transfer also, and we discussed the different kind of transfer processes like heat transfer processes, mass transfer processes, etc. Okay. After that, we defined our objective for this course, that was to quantify heat transfer in various systems. Then we talked about heat transfer in different phases, that is in the solid phase, in the liquid phase, in the gaseous phases, and we classified heat transfer into 3 main categories, that is conduction, convection, and radiation. These were the 3 modes of heat transfer that we will be predominantly looking in this course. Then the professor gave an overview of the course, that what all topics will be covered in the throughout the upcoming lectures. We will cover conduction, convection, phase change, that is taking heat energy and changing phases. Then we'll talk about radiation and also heat exchangers. These contents were explained in the first lecture, and subsequently in the second lecture, professor gave an introduction to conduction. We moved on to the first topic in our heat transfer course, conduction. So we talked about what drives conduction, that is a temperature gradient, and we talked about thermal diffusion, or it is another word for these conduction processes in solids and liquids. Then we talked about what is the importance for estimating heat transfer rate in systems due to conduction, and we talked about a constitutive relationship that we use for quantitating this conduction heat transfer, that is the Fourier's law. And we introduced a term called thermal conductivity, which is the constant that is relating the heat flux or heat transfer rate with the thermal gradient in all the materials. These are material properties, and also they depend on different conditions like temperature and pressure. Then we talked about we usually consider isotropic materials, in which we can maybe consider the thermal conductivity or the temperature gradient to be isotropic, like same in different directions. Then, but we also talked about non-isotropic materials, how they can have different thermal conductivities and how they can affect the final heat transfer rate in different directions. Then we made a general comparison about thermal conductivity in solids, liquids and gases, and we discussed about why solids have a higher thermal conductivity compared to liquids or gases. Then we introduced a term called thermal diffusivity, which, if you remember, was defined as alpha is equal to, can someone help me here? Do you remember the definition that we used for thermal diffusivity? Someone can.
Sir, it's K by rho Cp.
Yes, yes,
How is conduct to how it store capacity of storing?
yes. It is the ratio of thermal conductivity in a material with regards to the energy storage capacity of material, right? Yes. All these topics we covered. Someone wants to join. Let me admit. Okay. All these topics we covered in lecture 2. Then in the lecture 3 we talked about energy balance in different systems. This is a very important topic. This was a very important lecture, and we will be, throughout this entire course, we will be using this energy balance concept to solve our different problems. We talked about temperature distribution, the temperature gradient in different systems, and heat transfer rate, and we related them to the Fourier's law equation. The Fourier's law equation was, for a 1D system, if you are writing, we can say the heat transfer rate, say in x direction, is equal to minus of thermal conductivity, the area of cross section, into the temperature thermal gradient, right? These are important relations that you have to remember throughout this course. Then we talked about energy balance and diffusion equation. I think we derived, taking an infinitesimally small volume, we derived the diffusion equation, which said, like, which turned out to be something like this: del square T, which is the Laplacian operator, plus the heat generation term per unit volume divided by thermal conductivity is equal to 1 by alpha, which is thermal diffusivity, into the time variant of temperature, right? Then we need to use different boundary conditions to solve this diffusion equation. This equation we will refer to as diffusion equation. We need different boundary conditions, and in lecture 3 we also looked at different types of boundary conditions, which were like constant temperature boundary condition, or a constant flux boundary condition, or a variable flux boundary condition, which we also called as convection boundary condition. And then we talked briefly about Newton's law of cooling, in which case we said the heat transfer rate would be equal to the H into the surface area available for heat transfer into the temperature difference, delta T, H at delta T. These topics we were covered in lecture 3, and after that we moved on to lecture 4, where one-dimensional steady-state conduction was discussed. I think we took the example of a plane wall to derive the equations for one-dimensional steady-state heat conduction, and we introduced an important concept, which is the thermal resistance concept. This is very important, and in fact in today's lecture we will be extensively using this thermal resistance concept to solve our problems. Um, then yeah, not only conduction thermal resistance, we discussed also about convective thermal resistance also. We saw how to make resistance network in these lectures, and we briefly got introduction to composite walls and how we can build thermal resistance network for these composite wall cases. After that, we moved on to lecture 5. That was the last lecture in this week, in which we looked at an extensive composite wall, like which was made of different materials of different thermal conductivity, and how we can apply this resistance concept to simplify our problem. We also talked about an important quantity called overall heat transfer coefficient, and we also talked about contact resistances. Then towards the end, at the end of this lecture 5, we looked at till now we were looking at constant area of cross-section conduction heat transfer across constant areas. Then towards the end, we also looked at a varying area cross-section system for conduction heat transfer, taking the example of a truncated cone. These were the different topics that were covered in all the 5 lectures, and I hope everyone has gone through all these 5 lectures, because we would be using the different concepts that we learned to solve problems in this session. Today I would discuss about 5 problems briefly, and these problems, the way we solve these problems, it will help you solving the assignment problems that you have. Any questions till now?
Sir, tomorrow there is also session, or this is only this week session?
Oh, okay. In my understanding, for this course, there are 4. Let me admit someone. As far as I know, there are 4 problem solving sessions for this course. One already happened on Friday, and this is the second session on Monday and Tuesday, that is tomorrow. I think there will be 2 more sessions. It is not necessary to join all sessions. All the sessions would be almost similar, except that different teaching assistants would be taking different sessions. So to answer your question, yes, tomorrow also there would be sessions, problem solving sessions, but you can attend any one of these 4 problem solving sessions. Is that clear?
Sir,
Sir, this happen.
it means, sir, only 4 problem solving of all the 12 week.
What? No. Every week these problem solving sessions would be there. So for 12 weeks, every week there would be 4 different sections. Like, say if someone can't join today, they can join tomorrow. It is designed like that. Every week there would be 4 different sessions covering the same topic, but again, for all the 12 weeks, these 4 sessions would be happening.
Yes, sir. Correct, sir.
Yeah. So I will be taking session every Monday, and another teaching assistant would be taking sessions, say, every Friday, and another teaching assistant would be taking sessions every Tuesday, and so on. Okay. Are there any questions related to the contents of the first five lectures? If not, I think we can move on to the problems. You have already got the assignment questions, right?
Yes, sir.
Okay.
Yes, sir.
Then I will go to the first problem. I think it would be helpful for you if you solve the problems along with me, because that will help you in solving your assignment problems later. Okay. You can see the first problem on screen. Just take 2 minutes to go through it. I will read the question for you. Consider a steady state conditions for a one-dimensional conduction in a plane wall having a thermal conductivity K is equal to 50 watts per meter Kelvin and a thickness L is equal to 0.25 meters with no heat generation. If T2 is shown here in the figure, if T2 is equal to 30 degrees Celsius and dt by dx, that is the rate of change of temperature in the x direction, equal to 200 Kelvin per meter, then determine the heat flux and temperature T1 as shown in the figure. Just take a minute to comprehend the question, then we can see how we will solve this problem. Is the question clear for everyone? What is given and what is being asked to us to find out? If someone has any queries in this question, please ask now. If not, I will proceed to.
Sir, this dt by dx means?
Okay, dt. Okay. Then let me start from the beginning. dt by dx is the rate of change of temperature in the x direction. How temperature varies in the x direction. This is the x direction that is shown here. You can see the x direction, right? The shaded area is the plain slab that is given to us, the shaded area, and T1 is the temperature of this plain wall at the left surface, and where x is equal to 0, right? And T2 is the temperature of this wall at the right surface, that is where at x is equal to L. dt by dx means as we move towards x is equal to 0, from x is equal to 0 to x is equal to L, how the temperature varies. Rate of change of temperature with respect to x. I hope that's clear.
Yes, sir.
Yeah, particularly in this case, when we say dt by dx equal to 200 Kelvin per meter, we are just saying that if we move say 1 meter in the x direction, the temperature would change by 200 kelvins. Clear?
Yes, sir.
Okay. Any thoughts on how to solve this problem? How to approach?
Fourier law using?
Yes, right. So I will list down whatever we know. We are being given T2 is given to us. T2 equal to 30 degrees Celsius. And L is given to us. L was given to us as 0.25 meters. Right? Then dt by dx is given to us as 200, right? Yeah, 200 Kelvin per meter. Apart from this, we also know the thermal conductivity of the material. Thermal conductivity of the material was 50. What is the unit for thermal conductivity?
Watt per meter Kelvin?
Yes, right. And we have been asked to find out the heat flux and the temperature T1. We need to find heat flux in the x direction and temperature T1. As someone rightly pointed out, we can use Fourier's law of conduction, which states that the heat flux in the x direction equal to minus of K into dt by dx, right? Remember that since I am talking about flux, this is per unit area. I don't have to include the area term again. So we can directly compute. Can we directly compute heat flux from here? Do we have all the values? We have thermal conductivity value. Someone has given an answer, but check that answer, because be careful of the sign conventions. this is 50 watts per meter Kelvin into dt by dx was 200 Kelvin per meter, which would give us minus 10 kilowatt per meter square, right? I see some answers in the comments. Yeah, people are saying 10 kilowatt plus is equal to minus 10. Okay, whenever you write these answers, be careful of the sign conventions and also of the units. Okay, heat flux, someone wrote it as kilowatt, but heat flux is per unit area, so it should be kilowatt per meter square. Someone simply wrote minus 10 and it should be minus 10 kilowatt per meter square. Yes, I think most of you have got the answer. Is there anyone who hasn't got this answer? Okay, I think everyone.
Sir, this T1 temperature, input temperature.
Yes, T1 we will find out. We just now found out the flux, and now we will go to find out the T1. Can someone give an expression for dt by dx, which involves T1 and T2? We studied this in one of the lectures when we were doing one-dimensional steady-state heat conduction problem. Does someone remember? For this particular case, T1 minus T2 by L. Yeah, it would be T2 minus, in this case, T2 minus T1 by L. If you are confused how this expression came, maybe we can try to derive this expression from the first cases. Do you want me to derive these expressions?
Yes, sir.
Okay. We can start from the thermal diffusion equation. What is the thermal diffusion equation? Del square T plus heat generated per unit volume divided by K equal to 1 by alpha dot T by dot T, right? This expression you should remember, and I think this expression we derived using energy balance in lecture 3 probably. So in this expression, which all terms we can neglect? Just look at the question once again. It is saying it is a steady state condition. What do you mean by steady state condition?
Right term 0.
The right hand side would be 0. Steady, because steady state means there is no change with respect to time, right? Right hand side is the rate of change of temperature with respect to time. So when we say steady state means this change of temperature with respect to time goes to 0. Then it is a one-dimensional system. What do you mean by one-dimensional system? Where can I incorporate this change in this equation?
Only one dimension, like x.
Yes, because del square would mean dou square by dou x square. This is the Laplacian operator, right? Dou square by dou y square plus dou square by dou z square, right? When we say 1D, we can neglect these two. Dou square t by dou y square and dou square t by dou z square would go to 0. So this del square t term, we can simply replace it by dou square t by dou x square term. That is the implication of one-dimensional conduction. Then if we read through the question again, it is also saying that there is no heat generation in the system, right? How does that affect our equation, the governing equation?
Second term will be 0, sir.
Yes, right. Because this is the Q dot is the heat generation per unit volume. When we are saying there is no heat generation, that term will also vanish to 0. So this thermal diffusion equation simply reduces to dou square T by dou x square equal to 0 for this case, right? Now what we can do, we can integrate this, right? We can integrate this expression twice. I can write d, since it is no more a partial derivative, it is varying only with respect to x. So integrating it once would mean dt by dx is equal to c1, right? A constant. Someone wants to join, let me admit. Is there any confusion? And if we integrate it further, it would mean that temperature T equal to C1x plus C2, right? Now these are the equations we have, and we can substitute our boundary conditions in these equations. Is there any confusion?
No, sir.
Okay. What are the boundary conditions we have? One boundary condition is that we know at x equal to 0, temperature is T1, right? Then we can write from this equation T1 equal to x equal to 0 means this term would vanish to 0. Simply it is equal to C2, right? C2 becomes equal to T1. Okay. Similarly, at x equal to L, the temperature becomes T2. So I am writing it here. This is for at x equal to 0, then at x equal to L, we can write from this equation temperature T becomes equal to T2 is equal to C1 into x becomes L plus C2. C2 we already know that it is T1, right? Then simply rearranging, we can see that C1 equal to T2 minus T1 by L, right? And what is C1 actually? C1 is dt by dx. This is the expression that we wanted. This shows that dt by dx is linear in this plane slab for the given conditions. Is there any confusion? Or is everyone clear how we got this expression?
Yes, sir.
dt by dx equal to T2 minus T1 by L. Or should I write it better? Is it clear?
Yes, sir. It is clear, sir.
Okay. Then I will move on. We know that dt by dx equal to T2 minus T1 by L, and dt by dx is already given to us, right? It is where's dt by dx? Yeah, it is 200 Kelvin per meter. 200 equal to T2 is already given, 30 degrees Celsius minus T1. We don't know, we need to find out T1 by L. L is also given to us, 0.25 meters. So from this we can solve for T1. Can someone tell me what T1 is? Solving this equation. .200 into 0.25 is 25 to 50. 30 minus 50 minus 20 degrees Celsius, right?
20
or minus 20?
minus 20, sir.
Yeah. So we have solved the first question. Just read the question again and see if you are able to um, digest it completely, and the question and the solution process. If you have any confusions, just ask me now itself. The question is clear, I think, and the solution process is pretty straightforward, right?
Yes, sir.
Okay.
Sir, why this sir, why this Q flux is negative? Because T1 is less than T2.
Yes, yes. In this case, we have considered x to be positive in this direction, right? In this direction. But T2 we got it as what, 30 degrees Celsius, and T1 we got it as minus 20 degrees Celsius. So in which direction is the heat flow happening? The opposite direction, right? As to x, right? From higher temperature to a lower
Yes.
temperature. So that is why the heat flow we are getting negative, because x we consider to be in towards the right direction, whereas the heat flow is happening in the opposite direction.
Sir, can we solve T1 temperature using this Fourier equation also?
E-
Just put the value dt by dx to T2 minus T1 upon L.
yes, yes, you
Is
can.
the same or
Yes, it is the same. Uh, we'll
at
write.
that?
I will write this equation again here. Mm, Q of x would be minus 10 kilowatt per meter square, right? So it would be like, if I
10
write
raised to
it in
4.
terms of watts, it would be minus 10,000, which is equal to minus of k. Where is k? Minus 50 into dt by dx. T2 T2 is given, right? 30 minus T1 by 0.25. Can someone solve this?
Sir, here why you write? Okay.
Is that okay?
Sir, I have one confusion. Whenever we write dt, means T1 minus T2 or T2 minus T1?
Uh, Give me a moment. Someone wants to join the call. Let me admit the admit. Okay, what was the question?
Sir, I am saying that what is the dt value, like T1 minus T2 or T2 minus T1?
If you are writing dt minus
How
d,
to decide?
if you are writing dt minus dx, it would be like the final temperature minus initial temperature in the direction we are considering. In this case, if I want to say x is in this direction, then I would write dt minus d. I would write dt as t2 minus t1.
Question answer is minus 20.
Yes, yes. Answer is minus 20 degrees Celsius. Uh, okay, you are saying by solving this equation, both are the same equations, right?
Okay, okay, understand, sir.
Yeah.
Thank you.
This equation and this one will turn out to be the same, because 10,000 by 50, it will be 200, right? Yeah, it will be the same equation. We can approach it both ways, as you rightly pointed out. Okay, any further questions on this? If someone if there is no further questions on this question, I think we can move on to the next problem, right? Okay, I think that's a yes. No one is responding, so I would move on to the next problem.
Yes, sir.
Yeah, thank you. I'll read the problem. An apparatus for measuring thermal conductivity employs an electrical heater. Say it is saying this is an apparatus for measuring thermal conductivity, whatever figure that you see on the right side, and it employs an electrical heater. Electrical heater. The electrical heater is placed here. There's black um, black marking on the figure, sandwiched between two identical samples of diameter 30 mm. So this electrical heater is sandwiched between two samples. This is a cylindrical sample of diameter 30 mm, and this is also a cylindrical sample of diameter 30 mm. Both are identical. Diameter is 30 mm and length is 60 mm. Okay, diameter is 30 mm, diameter is 30 mm and length is 60 mm. This is what you need to understand. Then, which are pressed between plates maintained at a uniform temperature T0 equal to 77 degrees Celsius. These samples are placed between two plates. These are the plates, and they are maintained at a uniform temperature T0 equal to 77 degrees Celsius by some means, by a circulating fluid. Okay. Now, a conducting grease is placed between all the surfaces to ensure a good thermal contact. We'll come back to this point. And differential thermocouples are embedded in the samples with a spacing of 15 millimeter. So now we have two samples. One sample is here and one sample is here. And differential thermocouples are placed in these samples. Differential thermocouple means it will measure thermal temperature at 2 points, say 1 point here and 1 point here, and it will report the difference in temperature between those 2 points. It is saying that for this differential thermocouple, the spacing is 15 millimeter, which means it is measuring temperature difference between 2 points which are 15 millimeter apart. Okay. Then the next thing that is given to us is the lateral sides of the samples are insulated to ensure one-dimensional heat transfer through the samples. The sideways are all insulated. That means whatever heat is being generated in the heater is traveling in one dimensionally, like either directly upwards or directly downwards in the vertical direction. That is the only dimension that we are interested in. Okay. Now with two samples of stainless steel 316 in the apparatus, means both the samples are identical and made with SS316, stainless steel 316, and it is also given to us that the heater draws a certain amount of current, and it is operating at a certain voltage, 0.353 ampere current and 100 voltage, and also the differential temperature that is indicated by these thermocouples is also given, which is again same in both cases, like 25 degrees Celsius, same as here 25 degrees Celsius. Now for such a given configuration, we are being asked to find out the thermal conductivity of the stainless steel sample material. That means this cylindrical sample material, we need to find out the thermal conductivity. Just read through the question once, take 2 minutes, try to understand the question, and if you don't understand the question, just let me know. Go through the question once. Is the question clear for everyone? I just want to ensure that everyone knows what is given in the question and what we are being asked to find out. If the question is not clear to anyone in any particular areas, just let me know. Muhammad Ijaz is asking a question in the chat window. Normally heat is transferred from high temperature to low temperature. Is it happen without any external energy? This temperature difference is the driving force for heat transfer. Say it is the difference in potential, right? For any transfer processes, like say for mass transfer, there should be a difference in concentration gradient, and for a current electrical energy to transfer, there should be a difference in electric voltage. There should be potential difference. Whenever there is a difference in potential, or in this case whenever there is a difference in temperature, there would be a heat flow. That is the driving force for the heat flow. Okay, we will come back to this question. Is the question clear for everyone? Can someone reply with a yes?
Yes, sir.
Okay.
Sir, is there any time to travel this current or voltage?
Yes, there is time. Right now, in this first week, we will be looking at the steady state processes. Like there will be an initial amount of time in which the processes would be transient. All the temperature changes would be with respect to time, and after some time, it will attain a steady state where it will no longer vary with time. Right now we are looking at only those steady state processes. These unsteady state processes where this temperature difference or this temperature everything is varying with respect to time, we will cover those in upcoming lectures. We will slowly increase the complexity. Right now we are looking at steady state processes where there is no change with time, and we are looking at one dimensional processes where heat transfer is occurring only through one direction. In the coming lectures we will add further complexities. We will go for unsteady state processes where temperature varies with time, and we'll go for two-dimensional heat transfer where heat is transferring in not only one dimension, both x and y directions probably. Like that we will go on increasing the complexity of the situations. But for this week one, we look at only steady state and one-dimensional heat transfer. Okay.
Okay, sir.
Yeah. So I will explain the question. We have a heater here which is generating some heat, and we have sample material identical on top and below, which is made of stainless steel. For which the diameter and length are given, and at the top and end of the sample materials the temperature boundary condition is specified with I think the plate temperature is equal to 77 degrees Celsius. 77 degrees Celsius. Further, differential thermocouples are placed in the sample materials where it measures the temperature difference in a small area delta x, not small area, small length, delta x equal to 15 millimeter. It is saying there is a temperature difference of 25 degrees Celsius, and we are being asked to find out the thermal conductivity of the material. Can someone tell me how can I proceed to solve this problem? There is a hint given. You can go through that also. It is saying half the heater power will pass through each of the samples which are presumed identical. How can we use that information to simplify our problem? Okay. See, there is some heat generated in this heater coil. Everyone agrees, right? Can we get an expression for that heat generated heat?
I square RT, electrical power.
Yeah, it is joules heating, right? It could be
Yes.
I square R. I square RT would be, what is it called, I square RT? It will be joules, right?
In terms
But
of what?
we need in terms of watts, power in terms of watts. But do we have R term here, the resistance of this heater material here, given in the question? No, we have voltage and current, right? So this is equivalent to V square by R, or is equivalent to VA, right? We have studied this Joule's heating law, right? People are joining. Let me admit them. Any confusion in here? This is the amount of heat generated when through Joule's heating, when an electrical current is passed through a material. So we know the voltage and current in this case. Oh, sorry. See, we know the voltage and current in this case, which is 100 volts and 0.353 ampere. So we can say, which is equal to 100 into 0.353 ampere, which is equal to
35.3
35.3 with the units of
watt.
watts, right? We know the heat generated in this heater material. Now, where does this heat go?
Half up on the both the sample.
Yes, this heat generated will will be dissipated like on both the ways. Like it will be dissipated to the sample on top, and it will be dissipated to the sample on the bottom equally. By equally, because all the conditions are identical, right? The samples on top and bottom are made with the same material. They have the same diameter. They have the same length, and also the end boundary conditions are also same. End boundary conditions are, it is maintained at 77 degrees Celsius and 77 degrees Celsius. So we can say all the conditions above and below this heater coil are identical. So whatever heat is generated, half of that heat will be transported in the upwards direction, and the remaining heat will be transported in the downwards direction, right? So we can simplify this problem by considering only half of this problem domain. So I'm considering, let me admit someone wants to join. Okay, so we can simplify this problem considering only the half portion. Is that part clear for everyone? That is what the hint was saying earlier. You saw a hint, right? Half the heater power will pass through each of the samples which are presumed to be identical. Is the simplification clear? Can someone confirm? Is it clear?
Yes, sir.
Okay. Then again we can write the Fourier's law, which is saying heat transferred is equal to thermal conductivity times area of cross section times the temperature gradient, right? Right? In this case, the heat that we are interested is not the complete Q, it is the Q by 2, because half the heat is being transferred to sample above and half the heat is being transferred to sample below. And this minus quantity will come back to this later. K is the thermal conductivity of the material, right? What is the expression for area of cross section of the sample material?
Pi r square.
Pi r square, yes. And we have been given that value, right? Pi r square or pi by 4 d square. We have been given d as, what was d?
30 mm, sir.
30
D.
mm, yes.
Sir, it's maybe I think pi r square L, sir. It's cylinder, na?
No, this is the cross sectional area, not the surface. Okay. Don't get confused there. We are interested about this area because heat is being transferred perpendicular to this area, right? Heat is being generated here, so it is being transferred in this direction.
Okay, sir.
In this Fourier's law, it is the cross-sectional area that is perpendicular to the direction of heat transfer. Okay?
Okay, sir.
Okay. It is pi by 4 d square. It was 30 mm. And dt by dx. Do we know dt by dx for this material? For this process? I will go back to the question. Do we know dt by dx?
Yes, sir. This T1 will be 0, T2 25 divided by length.
T1 will be 0, T2 will be... Can you repeat that?
T2 will be 25.
Yes, no need to say T1 would be 0. Yes, you are right. See, we just told that it would be a linear temperature profile, right? So, in steady state one-dimensional heat transfer without any heat generation, if say this is T1, some value, and say this is a higher temperature T2 on the right, then dt by dx would be linear. Let me admit someone. Okay, dt by dx would be linear. So that would mean dt by dx could be say suppose this whole length is L, it could be T2 minus T1 by L, or it could even be, what does this dt by dx signify? It is the slope, right? It is the slope of this line.
Yes, sir.
So it is not necessary that I have to go for these n temperatures. Even if I take any two temperatures in between, say, and I get a temperature difference as delta T in a length of delta X, then that also is dt by dx. Sorry. Do we have these values given in the question? Is it clear what I was trying to say? This dt by dx is the slope of this linear temperature profile, and it would be the same irrespective of where we are going to measure it.
Sir, 77 T0 as mentioned and T2 also mentioned 25.
77 is mentioned. Okay, T2 you are saying 77 is mentioned. What was 25? 25 was not T0, right?
T0 is 77, sir.
Say in this case is suppose uh, say okay, say T1 equal to 77 degrees Celsius. T2 is not given to us. What was this 25? 25 was not T1. It was a delta T somewhere in between. Right?
Sir, it is mentioned delta T1 25 or delta T2 25 degrees centigrade.
Delta T by it is this quantity. It was 25 by 15 mm. 25 by 15 mm. 0.015. I want you to be clear about this part. Why dt by dx is 25 by 0.015. Let me know if that is clear for you. Think about it. If we can write dt by dx as 25 by 0.015. Look at this diagram and look at what this thermocouple junction is giving us. It is giving us the temperature difference between two positions. This difference in these positions is delta x, that was given as 0.015 or 15 mm, 0.015 meter, and the temperature difference between those 2 points is delta T, given as 25 degrees Celsius. Is that clear?
Sir, I have one doubt.
Okay.
This 77, it is not happening that from the heater.
No, that 77 is being okay, we'll go back to the question. What is 77? 77 is the temperature of a plate that is at the end of this sample, kept at the end of this sample, which is maintained at 77 degrees Celsius using some fluid flow, right? Yeah, a circulating fluid flow. That is the boundary temperature for the plate. Yeah, if we knew this temperature of this heater, then yes, we could write say this heater temperature minus 77 degrees by whatever the length of the sample was. But we don't know the heater temperature, right?
Thermocouple temperature is 25, sir, no? So initial temperature is 77. By the time it will reach to thermocouple, that delta T1 is a 25.
No. Don't think of like that. Don't think of, there is no time change of, there is no, it is a steady state process. The temperature at each cross section is remaining same with respect to time. Thermocouple, it is reading the steady state temperature, not the transient temperature in this case. Say, okay, I will draw it again so that it is clear. Heater is here, it is producing some heat, and say it has some temperature T2 that we don't know, and this heat is being transferred to the through the sample, and at the end of the sample there is a plate which is at a temperature of 77 degrees Celsius, and we are given a hint. We are given a hint that thermocouples are placed at two positions, and the temperature difference at these positions is measured. This distance is 15 mm, and the temperature difference at this distance is delta T equal to 25 degrees Celsius. Is it clear what the thermocouples are measuring? It is just measuring the temperature difference between two positions in the sample. Okay, so dt by dx could be either, as I mentioned, t2 minus or t2 minus t1 by L, or it could be this temperature minus this temperature, that is delta T, by this length minus this length, that is delta X, since the temperature profile is linear. It is the same slope everywhere in the sample. You can, if it is not clear yet, you can go through it later. Is it clear now, like with this explanation?
Yes, sir.
Yes, sir.
Okay, then dt by dx we can replace it with,
Sir, I have one more small doubt.
yes,
That distance between two thermocouple is 15 mm, or one thermocouple distance is 15 mm.
It is a differential thermocouple, so that thermocouple itself has two leads. Both those leads are measuring temperatures which are 15 mm apart. So in the image, wait, let me admit someone. So in the image, if I want to show this, this is 15 mm, this distance. It is a differential thermocouple.
Okay.
And it has two leads, and the difference between those two leads, what is it measuring, is 15 mm.
Correct, sir.
Clear, right? Clear, right?
Yes, sir.
Okay, so dt by dx, okay, the q by 2 heat would be transferred to the sample with a thermal conductivity of K, with an area of cross section of 30 millimeter, pi by 4 d square, and with a temperature gradient of 25 by 0.015 meters. Here I am not using this minus sign, you might have noticed, because here I have not specified any specific x direction. So this dt by dx is like an amplitude value, modulus value. It is the rate of change of temperature with a given difference in sample length, not in any particular direction. It is the, in whichever direction it is just taking the magnitude value. So we don't have to take the sign convention in the picture. We know all the values in this case. Q we already found out 35.3 watts. Can someone substitute and tell me what is the thermal conductivity of the sample material? I think it is a straightforward calculation.
Answer D, sir. 1.5 into 10 power 1 watt per meter Kelvin.
Yes, you are right. The answer is 1.5 10 to the power 1, or 15 watts per meter Kelvin. I would suggest everyone to try to go back and check this concept again if you are not clear with this. But right now we will move on to the next problem. Is that okay?
Yes, sir.
Okay. But rest everything is clear, right, in this problem? Why did we take the symmetry into consideration, how we simplified the geometry into two parts, and how we applied Fourier's law to get the final thermal conductivity of the material, right? Okay, now I will move on to the third problem. Okay, there is no figure given here, you can just read through it. A new building in a cold climate area is being designed with a basement with an L equal to 200 millimeter thick wall. There is a building in a cold climate area and it has a basement with wall thickness 200 millimeters. Let's try to draw that. There is a wall 200 millimeter thick. Inner and outer basement wall temperatures are Ti equal to 20 degrees Celsius. Say this is the inner surface of the wall, this is the wall, okay. This is the inner surface which is at 20 degrees Celsius and this is the outer surface which is at 0 degrees Celsius. So the inner is at a higher temperature and outer surface is at a lower temperature, so heat transfer will occur from inside to outside. The architect can specify the wall material to be either aerated concrete block or stone mix concrete. So now for the person who is building this wall, the person has two options. They can either go for aerated concrete to build this wall or they can go for stone mix concrete. For both of these materials, the thermal conductivity properties are given. For stone mix concrete, it is 1.4 watts per meter Kelvin, and for aerated concrete, it is 0.15 watt per meter Kelvin. So, to reduce the heat transfer, which material to reduce the heat loss from inside to outside, which material among these two should I use to build the wall? Can someone comment on that? Just by looking at the thermal conductivity values of these two materials, can we say which material is preferable purely in terms of reducing the heat loss?
Polystyrene sheet, sir.
Okay, don't go for polystyrene sheet.
Aerated concrete. Aerated concrete.
Okay, yeah, aerated concrete has a very low thermal
Less
conductivity,
thermal conductivity.
so heat loss would be minimum, right? Okay, now you can look at the first question. To reduce the conduction heat flux through the stone mix wall, the person has already gone for stone mix wall. Say they have gone for stone mix concrete, so the heat loss is high, right? Thermal conductivity is high, so heat loss is high. Now they want to reduce this heat loss to a level equivalent to that of the aerated concrete wall. And for that purpose they are going to add polystyrene sheet to the already built stone mix wall. And the question is, what should be the thickness of this polystyrene sheet that should be added to this stone mix wall to make its heat loss equivalent to that of aerated concrete block? Is the question clear for everyone? Read only the first part of the question. If the question is not clear, I will explain again. I will anyway explain. I think there is some confusion. Okay. There is a basement and it has got a wall. Say this is sorry for the poor drawing. And inner temperature is 20 degrees Celsius. Inner wall temperature is 20 degrees Celsius. Outer wall temperature is 0 degrees Celsius. There are two cases. In one case 20 degrees Celsius, 0 degrees Celsius. In one case this material is what? stone mix concrete, stone mix concrete. In the second material, in the second case, this material is aerated concrete. Aerated concrete. So we know that for stone mix concrete, heat loss is high, right? Heat loss is high, and for this case, heat loss is low. Do you agree on that? Comparing the thermal conductivities. Is that clear?
Yes, sir.
Now the purpose, our purpose is, we have already built a house with this stone mix concrete. So we know that our heat loss is high, but we want to bring down this heat loss to a level that of aerated concrete material. Okay, we want to minimize the heat loss. For that purpose, we are going to add some another material, that is the polystyrene sheet. We are going to add some polystyrene sheet. Say this is polystyrene sheet material. We are going to add that, so that the combined resistance to heat flow is equivalent to that of aerated concrete. Is that clear?
Yes, sir.
Okay. Now we want to find out what would be the thickness of this extra polystyrene sheet that we should add to stone mix concrete, so that their combined effect would be equivalent to that of aerated concrete. Can someone suggest a solution strategy?
Sir, we need to write the equations. We need to equate the amount of heat conducted through the aerated concrete, that is equivalent to uh, for the second case. So we have considered the polythene sheet. So we need to do the energy balance, sir. So by doing the energy balance, we need to find the thickness.
Okay, but yes, you are right. We need to, in both the cases, what is equal? The heat flux, we are trying to make it equal, right? The heat loss, we are trying to make it equal. So
Yes, sir.
yeah, uh, in such cases, this is like a composite wall case, right? We can make use of the resistance concept that we used. Do you remember that? Say,
Yes, sir.
yeah, say this is 20 degrees Celsius here, and this is 0 degrees Celsius here. The resistance to thermal transport, or the resistance to heat flow offered by this aerated concrete, we can model that by a equivalent thermal resistance, right?
Yes, sir.
And what is the, do you know the thermal formula for that thermal resistance for such cases?
L by Ka.
L by Ka, yes. L by Ka if you are talking about heat transfer rate, but if you are talking about heat fluxes, because we know that here A is not given, right? Area of cross section is not given. Either you can take it using unit area of cross section, or you can just mention in terms of heat fluxes. We can say it is a uniform area of cross section and heat fluxes are equal. So say this is the heat flux, and in that case the thermal resistance would be L by K, right? Is that okay? Or if
Yes, sir.
if you're taking L by Ka, you can keep A as 1 unit area. Okay, and in this case, in the next case, again we have end temperature as 20 degrees Celsius and end temperature as 0 degrees Celsius. But here we have two materials, right? So they will offer two resistances. This resistance was offered by the polystyrene sheet, and the next resistance was offered by the stone mix concrete. So again, similar to this, we can write the equation as say L is the length of the wall. Say this is stone mix concrete, this is polystyrene sheet, this is aerated concrete. The length of stone mix wall remains the same, it is L, and thermal conductivity of stone mix concrete, thermal conductivity of aerated concrete. And I should not write this as L. This is what we need to find out. We need to find out the thickness of polystyrene sheet that should be added. So the resistance, okay, someone wants to join. We need to find out the thickness of polystyrene sheet. So the thermal resistance of polystyrene sheet would be again the length by thermal conductivity of polystyrene sheet. Is this resistance circuit clear? Is this clear for everyone?
Sir, that whatever the fluid is flowing inside and outside, and that H value we require to take or not?
In this case, it might have mentioned that it is not mentioned anywhere, right? So it could be negligible. Even if it is given, we know that we don't need those values. We know the temperature at this point, okay, at the beginning and end of the world. We know those temperatures, and we just need to find out the thickness of this polystyrene sheet. So since all these resistances are in parallel, we can write from here, say Q dash equal to 20, this temperature difference 20 minus 0 by this thermal resistance. Even if we have some fluid flow, like some fluid flow here, we can write there will be another temperature for that fluid. Say I can, okay, anyway, since you asked that, I will draw it here. This, say this is aerated concrete, say this is 20 degrees Celsius, say this is 0 degrees Celsius here, and say some fluid is flowing with a temperature of T infinity equal to, say, minus 2 degrees Celsius and some H value. Then in such cases the circuit would be 20 degrees Celsius. Okay, someone wants to join. Okay, 20 degrees Celsius, 20 degrees Celsius, 0 degrees Celsius, and minus 2 degrees Celsius, right? This would be L by K of aerated concrete, and this would be, in the case of convection it is 1 by H. 1 by H. So if the heat flux is Q double dash, we can write Q double dash equal to either 20 minus 0 by L by K of aerated concrete, or it is again equal to 0 minus 2 divided by the resistance in between them, and we can keep on writing like that. So for the question at hand, that part is irrelevant to us because we need to find out only T, and that we can find out the thickness of polystyrene sheet, and that we can find out with this, only this information. Is that clear?
Yes, sir.
Okay, so in this case how can we find out? We know that the fluxes are equal. So flux in this case we wrote it as 20 minus 0 by L by KAC, and flux in this case we can write Q dash equal to again 20 minus 0 by T by thermal conductivity of polystyrene sheet plus these are resistances in parallel, right? So these resistances we can add up directly, right? Stone mix concrete. So we want to make this Q dash equal. So if you equate 1 and 2, we can get the expression, we can get the value of thickness, because we know all other values. Length value, I think we know. Length was 200 mm, length of the wall, and all the three thermal conductivities are given. So we can equate L by KAC aerated concrete equal to L by thermal conductivity of stone mix concrete plus thickness by thermal conductivity of polystyrene sheet. Okay, from this expression we can get the thickness value. Is that clear for everyone?
Yes, sir.
Okay, has someone already calculated the value and found the answer? We know all the values. You can also calculate it later. Is someone calculating? Let me, if there is some answer.
Sir, can you bake this slide so that we can show this value?
Can I?
Sir, can you please go back so that we can see the value of
Okay, sure.
conductivity?
Sure. Okay, I think I have the calculator result somewhere here. It should be 32 millimeter. Is someone getting 32 millimeters?
0.032.
Yes, 0.032 meters, right?
Yes, yes.
Okay. Then yeah, our approach is correct. We are getting 32 millimeters at the thickness of polystyrene sheet that we need to add to make the combined heat loss in this case equal to that of an aerated concrete. The substitutions you can anytime do and get the results, but make sure that you understand the concept. Is there any confusion in the concept? What we were being asked to find out and how we approached the problem. Is there any confusion there?
No, sir. Clear, sir.
Okay. Then I think we can move on to the. Could you show the question again? Okay, I can show the question. Someone wants to see the question again. Ashad Basha, do you have some queries? Okay. Then we can go to the second problem.
Sir, can we receive this material or this document or presentation?
Yes, yes. These will be uploaded and the links will be shared.
Thank you, sir.
Yeah. It will not be me who is sharing. I will check with the coordinator, and I think the links are being shared. If it is not shared, I can make sure that you will get these links. It's no problem. I will make sure that you will get these materials. Okay. Then we can go to the second part of the problem. If the floor dimensions of the basement, it is a continuation of the same problem. If the floor dimensions of the basement are 20 meter into 30 meter and the expected rental rate is $50 per meter square per month, what is the yearly cost in terms of lost rental income if the stone mix concrete wall with polystyrene insulation is specified? Note that the area of the floor space is utilized to calculate the rent. This is just a like like aptitude problem, not particularly heat transfer problem. It is just to let us know that while we are trying to make these additional insulation layers, what is the compromise that we have to make in terms of other expenses. Is the question clear to everyone? Okay, I will explain the question. In the same problem, say this was our floor area before, 20 meter cross 30 meter. Okay, 20 meters cross 30 meters. This was our floor area, and we had a wall. Okay, it was a rectangular room. Okay, and for our heat transfer requirements, we reduced this floor area, right? We added additional insulations, so it is no longer 20 meter cross 30 meters. It is no longer 20 meters cross 30 meters. We added some insulation, further insulation to this. So the available floor area is further reduced. Is that clear? To relate it to our previous problem, say this was the outer layer was stone mix concrete wall, and the inner layer is polystyrene sheet wall. Okay, they are saying initially it was like, if there was no polystyrene sheet, it would have been a 20 meter cross 30 meter floor area, and with polystyrene sheet we already found out the thickness. This thickness is 32 mm wall. It is no longer 20 meter cross 30 meter. It would be 20 minus 2 times thickness cross 30 minus 2 times thickness, right? Say this is A1, say this is A2, area before insulation and area after insulation. We are losing some floor area, and if the rental charge is $50 per meter square per month, what is the lost income per year? That is the question. So we can just find what we can do. We can just find out A1 minus A2, and we can multiply that with 50 per month. It is per month, and we need answers in here. We can multiply that with 12, so we will get the answer, the lost income. it is not heat transfer question, it is a aptitude question, so I don't want to spend much time on it. You just make sure that you know what is being asked in the question and how we can solve it. Is it clear? Is the question clear first of all?
Yes, sir. Clear, sir.
And is the solution approach clear? Can someone give a respond with a yes or no?
Yes, sir. Yes, sir. Clear, sir.
Okay. I think I will tell you what answer we should get. If you do that, I think we will get an answer of $1920 per year. This should turn out to be the answer. You can check that later. Okay.
Okay, sir.
Yeah. Thank you. Now I will move on to the fourth problem. Yeah. I will read the problem for you. A block of solid ice T is equal to 10 millimeter thick. So this is a block of solid ice. This much area is a block of solid ice. Whatever you see within this, T is equal to 10 millimeter thick, has been kept in an isolated chamber where the bottom surface of the ice is maintained at T cold equal to minus 4 degrees Celsius. So this is the block of ice, 10 millimeter thick block of ice, where the bottom surface is maintained at a temperature of minus 4 degrees Celsius, and the top surface of the ice is exposed to a temperature T hot equal to 2 degrees Celsius. There is a temperature gradient between the top and bottom surface of the block of ice. So what happens, like we know that ice is at 0 degrees Celsius, like, and if the top surface is going away from 0 degrees Celsius, like to a higher temperature, ice will melt. So since the top surface is exposed to a higher temperature of 2 degrees Celsius, a layer of ice from the top surface has been transformed to liquid. Okay, creating a solid liquid interface as shown in the figure by a dashed line. So initially this was completely ice and the bottom surface was maintained at a temperature of minus 4 degrees Celsius, and the top surface is maintained at a temperature of 2 degrees Celsius. Since the top surface is at a higher temperature than 0 degrees Celsius, the top surface of the ice is melting, and this much portion has been changed from solid phase to liquid phase, and this dashed line shows the solid liquid interface. Is that part clear till now? Yes. Okay. Now the question is, determine the location of the solid liquid interface measured from the top at the steady state. Under steady state condition, that is no change with respect to time, we are being asked to find out what is this thickness, like what is this depth of this liquid layer that is formed. Assume one dimensional heat transfer. Again, it is on temperature is varying only with respect to, say, if this is x, temperature is varying with respect to only x, one dimensional, and it is steady state, which implies change with time is equal to 0, and we can neglect radiation, and we can neglect the convection for the purposes of this particular calculation that is being given in the question. Apart from that, we are being given thermal conductivity of solid ice and the liquid water. First, let me know if the question is clear. Yes, the question is clear. I hope it is clear for everyone. And can someone give me an approach so as to how we can solve this problem? See what all are being given to us. and see what we need to find out and how we can find out that. Any suggestions?
Sir, Q is equal to NCP delta T, equate to Fourier law Ka dt by dx.
Q equal to mcp delta t. Do we know all those values? Mm,
Sir, if we need to apply the heat flux equation between -4 to 0 and then -4 to 2. If you are equating, is it possible to find the unknown thickness, sir?
yes, yes, you are correct. It is possible. This interface, as you rightly pointed out, it would be at 0 degrees Celsius, right?
Yes, sir.
Yes. So we can again convert this into a thermal resistance network problem. That is what you are meaning, right?
Yes, sir. Yes, sir.
Okay. I will draw this in. Okay. I will draw it here. So at the bottom we have. Oh, sorry. At the bottom we have -4 degrees Celsius, right? Then there is a, say there is a thermal resistance of ice. Then there is this interface, that is this dashed interface, which is at a 0 degrees Celsius, right?
Yes, sir.
Above that there is a liquid film, and after that we have 2 degrees Celsius, right? This problem is reduced to a simple thermal resistance problem. Can someone say what is the resistance in this part? This resistance between -4 degrees Celsius and 0 degrees Celsius.
0 degree Celsius minus of -4 whole divided by that thickness, total thickness is 10. So unknown thickness, if you are considering as x, in the sense it is 10 minus x divided by thermal conductivity of the solid, that is equivalent to next one is 2 degrees Celsius minus of -4 degrees Celsius whole divided by total thickness is 10 divided by uh, the thermal conductivity of here solid and liquid is available.
Yes, yes, right. So it would be 10 minus x by the thermal resistance here would be the distance, that is 10 minus x by thermal conductivity of ice, and here the thermal resistance would be this unknown length x divided by thermal conductivity of liquid water, right?
Yes, sir.
And if suppose the 2 degrees Celsius to, okay, heat is flowing in this direction, yeah. If suppose say suppose we say flux is q double dash, we can say q double dash equal to 2 minus 0 divided by that resistance, that is x, which is the unknown that we need to find out, by k of liquid water that is equivalent to 0 minus -4, that is 0 plus 4 divided by the thermal resistance in between, thermal resistance of the solid ice, 10, that is 10 minus x by k of ice. Is that part clear? There was some question in between. Let me check. Okay, Ashad is asking 0. Yes, 0 would be the interface temperature, right? Because solid ice temperature is 0 degrees Celsius, and when the temperature goes beyond 0 degrees Celsius, it goes to liquid state. So the solid liquid interface temperature would be 0 degrees Celsius. Is that part clear, Ashrad? Okay. Is this equation thermal resistance concept clear for everyone?
Clear, sir.
From this we can find out the unknown x, right? Because we know all the temperatures, we know the thermal conductivity of liquid water, and we know thermal conductivity of solid ice. The only unknown is x. So since we are running a little short of time, if the concept is clear, I will just write down the answer here. If you solve this, you should get 1.31 1.3 millimeters. If someone wants to solve it quickly, just tell me if you are getting that answer. Thermal conductivity values also I can give. 0.569, 1.88, 0.569, 1.88. This is 0.569 watt per meter Kelvin. This is 1.88. Can someone solve and tell me if you are getting this answer, to make sure that we are doing everything correctly? Is someone calculating it? I can try to calculate.
Answer is around 0.0013 meters, sir. 0.00.
0.0013. That is, yeah, that is 1.3 millimeters, right?
Yes, sir.
X is equal to 0.0013 meters, right? Okay, then our approach is correct, and the answer is 1.3 millimeters. What is x? That is the thickness of this liquid water layer that is formed due to the exposure of this solid ice to a higher temperature than 0 degrees Celsius. I hope the solution and the question and the solution approach is clear for everyone. If anyone has some doubts, you can ask now for this question, problem 4.
Sir, if suppose thermal conductivity value not mentioned here, is it possible to assume, or otherwise we need to take some standard values and approach the problem, sir?
Usually in for most of the standard materials like solid ice, like air or air materials, water properties, air properties, or standard materials like stainless steel, all those people have over the years extensively have done experimentations and documented all the thermal conductivity values, specific heat values for different temperature and pressure conditions, for many materials and under many conditions. Usually we refer to, in practical cases, we refer to those tables to get these values. But if it is a new materials, yes, it would be difficult, for which if it is new material for which we don't know thermal conductivity, then we will have to go for approaches. First we will need to find out thermal conductivity. For that we will need to go for approaches as you see in this problem, right? In this problem we are making use of a non-heating source and a thermocouple to find out the thermal conductivity of the material. First we will need to find out the thermal conductivity of the material. If it is a very new material that we don't know of, then we will have to approach the problem this standard way. But yeah, for most commonly used materials, all these properties are already tabulated and they are fairly well available. Was that your question?
Yes, sir. Yes, sir. I got it, sir. Thank
Okay.
you.
Any other question? Is this question clear for everyone?
Yes, sir.
Okay. Then we will move to last problem for today. The question is a bit lengthy, but don't don't feel bad. We'll just read through the question. I think it's a simple question. Okay, the problem, I will read through the question, problem statement. Approximately 106, not 106, that's a mistake. It should be um, 10 power 6. Okay, approximately 10 power 6, that is like a million discrete electrical components can be placed on a single integrated circuit IC chip with electrical dissipation as high as 30,030 kilowatt per meter square. Like there are electrical chips in which there are many miniature electrical components and which produce lots of heat, electrical heat, as high as 30 kilowatt per meter square. The very thin chip, these chips would be very thin, is exposed to a dielectric liquid at its outer surface. What is a dielectric liquid? Okay, first let us go to this image. This is the chip we are talking about. On this chip, many small electrical components are placed and it is producing a large amount of heat, say 30 watt per meter square. And we need to dissipate this heat quickly, otherwise these electrical components would get damaged. For that purpose, we are using dielectric liquids on the outer surface of this chip. Dielectric liquids, their electrical conductivity is very poor and they will take away the heat very quickly from this chip surface. For this dielectric liquid, the properties are given. The H naught value, that is the convection heat transfer coefficient value, and the temperature of this dielectric liquid are given. That is the condition on the top surface. There is a chip, it is generating lots of heat, and to dissipate that heat, a dielectric coolant is being passed with a certain given heat transfer coefficient and temperature on the top surface. And the bottom surface of the chip, there is a board, say a circuit board. Yeah, this chip is joined to a circuit board. That is, this is the circuit board, CB. The thermal contact resistance between the chip and the board is 10 power minus 4 meter square Kelvin per watt. Okay, this chip and circuit board are joined by, say, some adhesive, and that joint has a thermal resistance. In our lectures we talked about contact resistances, right? This is similar to that. This is not the resistance of the circuit board or the resistance of this chip, it is the resistance of the contact between that chip and circuit board. Both the thickness and thermal conductivity of the circuit board are given. Thickness and thermal conductivity are given, and the other surface of circuit board, this board is exposed to ambient conditions, not of air, which is having a heat transfer coefficient of 40 watt per meter square Kelvin and temperature of 20 degrees Celsius. All these conditions are given. First, read through the first paragraph and understand what is given in the question, what are the conditions, where heat is being generated, and how that heat is being transported to different locations. Let me know if that part is clear for you.
Yes, sir. Sir, shall I try? Sir, now the air temperature is given. From air to board bottom surface, there is a convective resistance is there, and then followed by the control board on conductive resistance is there, and then thermal contact resistance is there, and followed by and convective resistance between chip and that liquid, sir.
Yes, but you didn't mention any conductive resistance for the chip material.
Yes, sir. I'm sorry, sir. That is also available, but that the thickness is not available here, sir.
Yes, you are right. We are neglecting that, as it is given that it is a very thin chip. This part is given to give us a hint that we can maybe neglect that thermal resistance in the chip material.
Chip material. Yes, sir.
It is also actually given here. We are being asked to give it is steady state conditions, one dimensional
Ne-
conduction, and negligible chip thermal resistance. It is given. So you are right. We can neglect that chip resistance. So yeah, I can see that one person has understood the problem. What about the others? Is the problem statement clear for everyone? Not the problem statement, the given scenario, heat generation and heat transfer scenario, is it clear for everyone? Yes. If so, we can look at the question. The question says under steady state conditions for which the chip heat dissipation is Q, the heat flux that is being dissipated from the chip is given. What is the chip temperature? Okay. Uh, the chip is generating some heat and it is dissipating some heat. We need to find out the chip temperature. Can someone guide me through how I can tackle this problem, or what is the approach to solve this problem?
QC double dash, that is 30,000 watt per meter square, that is equivalent to temperature of air minus coolant temperature, sir, divided by the total summation of resistance.
Okay, I will.
But anyway, sir, but I hope so it is wrong because both the temperatures are same. Then zero by anything zero, I hope we will get.
Okay,
So that's why we need to apply the boundary condition between air and that chip, that alone. Am I correct, sir?
okay. Like I will first draw the thermal circuit, then we will discuss it. Okay.
Okay, sir.
Could you show the question for a second? Okay, I should want to see the question for a second. I will go back to the question. Do you have some confusions, Arshad, in the question? I have taken a peek. Okay. So, if you didn't understand the question, let me know. I can repeat the question. Okay. The question just says this. This is a chip that is here. I am marking it here. The shaded area is a chip, and it is generating some heat. Heat flux Q double dash chip equal to 30,000 watt per meter square. 30,000 watt per meter square, and our purpose is to take away this heat. For that, a coolant is being passed on top of the chip, which has a temperature T infinity 0 of where is T infinity 0, 20 degrees Celsius, and H of 1000 watt per meter square Kelvin. Okay, T infinity 0 of 20 degrees Celsius and H0 of 1000 watt per meter square Kelvin. 1000 watts per meter square Kelvin. We are passing this coolant with these properties to take away the heat from this chip. Also, this chip is attached to a circuit board. This is a circuit board which has a specific thermal conductivity, say thermal conductivity to circuit board, and this attachment between these two, this interface also has a contact resistance or contact. And below the circuit board, air is flowing with a temperature of 40 and 20. Okay, T infinity I is equal to 20 degrees Celsius and HI is equal to 40 watt per meter square Kelvin. Okay, this is the question, and we are being asked to find out what is the temperature of the chip under steady state conditions. Is that clear, Asher?
Yes, sir.
Okay, so I will again, the easiest way to solve this problem is drawing an equivalent thermal resistance circuit. I will start from the coolant side. Say, okay, I can draw it as we see here. Say this is T infinity 0, that is equal to 20 degrees Celsius. Then there is a convective resistance, right? R convective is equal to 1 by H. HA in this case, since heat flux is given, it is 1 by H. So 1 by HO. Then we have the chip surface temperature, or since chip is given very small, we can say the whole chip has a same temperature Tc. Okay, then I will draw a resistance. What should be this resistance?
Contact resistance, sir.
Yes, that is the contact resistance between chip and the circuit board. And after this contact resistance, say we have some temperature at the top of circuit board. Then we have the sorry. Okay, this temperature we can say it is equal to, no, it is temperature at top of circuit board. Then what is this resistance?
Conductive resistance of circuit board.
Conductive resistance of circuit board, which we can write as
L by K. L by K.
The
L by K.
length of circuit board divided by thermal conductivity of circuit board. I think both of them are given. Then do we have any more resistances?
Convective resistance between air and the bottom of the.
Yes, we have convective resistance here, that is given by 1 by Hi, and this temperature is given as T infinity I is equal to 20 degrees Celsius, and say this is the temperature at the bottom of circuit board. Okay, bottom of circuit board. Now we have not specified the heat flux flow. Can someone say how heat flux is flowing? Because if you see at the end, as someone rightly mentioned, the temperatures are equal, 20 degrees Celsius and 20 degrees Celsius. From where to where the heat is flowing? Can someone help me?
Sir, from chip to whatever heat generated by chip.
Yes.
It is taken away by the coolant.
By coolant.
Yes. Actually, in chip, some heat is being generated. So this heat that is generated is flowing in both the directions, right?
Yes, sir.
Is that right? Correct, right? Yes. Now, can we okay, we know this H naught. I think we know this H naught. We know length of the circuit board. We know thermal conductivity of circuit board. We know Hi. We know T infinity I, and we know T infinity O. And we know actually the total heat flux that is flowing, that is generated in the chip. With all these values, can we find out the temperature of the chip Tc? Can you think about how we can write the how we can find the temperature of chip.
That heat flux divided by 2, which is equal to T infinitive naught minus Tc divided by 1 by H. Is it correct, sir?
Um, Heat flux divided by 2.
Is equal to temperature difference. Actually, higher temperature is Tc minus
Yes.
20 divided by convective resistance 1 by H naught.
Um, is the resistances equal in both the directions?
Need to take this air also and the circuit board also. This resistance we need to.
Yes, yes. Oh, he's saying all those are included. Okay, let me write it like this. Just tell me, can I write like this? That whatever the heat flux is generated in the chip, it is being dissipated to, say, Tc is the hot minus T infinity O by yes. Since in this case, um, okay. First, I will write this equation. Then we can have a discussion on this. By 1 by H naught plus the rest of the heat is being dissipated through the bottom side, Tc minus T infinity I divided by a combination of these three resistances. Since they are in parallel. Length of circuit board by thermal conductivity of circuit board plus 1 by Hi. Can I write it like this?
Yes, sir. Oh,
Um, from Is it clear for everyone how we wrote this equation? Whatever heat flux is coming is going in two ways, through the top side and bottom side, and just like how we add up the current in a electrical circuit, we can add up the flux that is being divided into different directions. It's clear, right?
yes, sir.
So in this case, the QC is given to us, TC is unknown, this is given to us, this is given to us, this is unknown, it is the same unknown, this is given to us, contact resistance is given to us, length of circuit board is given to us, thermal conductivity of circuit board is given to us, and this is given to us. There is only one unknown. We can find the temperature of chip, right?
Yes, sir.
Is it a lengthy calculation? Can someone solve it? Let me also try to solve it. Has someone solved it?
Please go back to the previous slides and the contact distance value I didn't take.
Okay.
Contact distance value.
Uh, Sorry, contact resistance is, okay, it is here, 10 power minus 4 meter square Kelvin per watt. Okay, if it is a lengthy calculation, we can do it later. I think you should get the answer as 49 degrees Celsius. That is what the answer I have. Um, but it is a simple substitution calculation, but just that it is a little lengthy, we can do it later if that is okay. Or has someone already got the answer? Shall I move on to the next part?
Yes, sir.
Yes, sir.
Okay, this problem has a second part. Now that we found the chip temperature, let's look at the second part of the question. Consider that air is used instead of the dielectric liquid. Like, where was the dielectric liquid? This was the dielectric liquid that we used initially. Instead of this, now they are proposing to replace this dielectric liquid with air, thereby reducing the convection coefficient approximately by an order of magnitude. Remember that dielectric liquid has a very high convection coefficient, when we replace this with air, our heat removal performance reduces drastically. It is being reduced by 2 orders of magnitude, the heat transfer coefficient. Previously it was 1000 watts per meter Kelvin. Now it is 100 watts per meter square Kelvin. Sorry, meter square Kelvin. Determine the value of the maximum allowable heat flux considering the constraint that chip temperature must not exceed 85 degrees Celsius. Okay, read this question. Let me know if you understand the question.
Sir, in the previous equation, instead of Tc, we need to put the value as 85 degrees Celsius. And then 1 by 40 already we put it. In that case, 1 by the new value 100, I think so. And in the previous slide, I am having one doubt, sir. So in this thermal conductivity of the circuit board, actually, sir, at the bottommost circuit board kb, that is equal to 32.4 watt per meter Kelvin is available. At the meantime, in the first paragraph, in the line, board thickness and thermal conductivity are LB equal to 5 mm and KB equal to 1 watt per meter respectively. That is available, sir. So the K value, thermal conductivity
Yes.
value of the board, we need to take it as 32.4 or otherwise 1 watt per meter. Which one?
Thank you for pointing it out. Uh, yeah, the reference question also has that mistake. Watt per meter kb equal to. So don't take this value. Oh,
Which one, sir?
wait. And the both thickness and thermal conductivity are. You can take this 32.4 watt per meter Kelvin as the value.
Okay, sir.
Thank you for pointing it out. This could be wrong. Because the unit is also wrong.
Yes, sir. Watt per meter Kelvin or meter degree Celsius, it is available as watt per meter only. That's okay, sir. Yes.
Yes. Yeah. Thank you for pointing it out. So is the second part question clear? Yeah, as you said, yes. We will use the same equation.
What about 85 degrees centigrade?
Yeah. We will use the same equation. In this case, the thermal resistance circuit is not changing, right? The known and unknown values are changing. Previously, TC was the chip temperature was the unknown, but now chip temperature is a known value, right? 85 degrees Celsius. The unknown value is the flux, maximum allowable flux. Now this is the unknown value. That is the change. And another change is that the dielectric liquid is changed with air. Now this H value will also change. All the other things will remain constant. Not remain constant, remain the same as previous question. Is that clear?
Yes, sir. And the H value, but that is mentioned as H naught. Actually, for us, the H value is what here we have considered as HI, sir. That's why we need to take the H value in the second part of the equation. Am I correct, sir? Because the fluid is what flowing at the bottom. Consider that air is used instead of the dielectric liquid. Okay, fine, sir. Fine, sir. At the top only.
Yes.
Okay, sir.
At the top and at the bottom, different uh, air. It is air itself, but it is being given as different H values. 40 watt. It could change depending on the temperatures.
Fine, sir. Understood, sir. Thank you, sir.
It is just a variation of the first part problem. Just that in this case, if we know the chip temperature, a maximum allowable chip temperature, how we can find the maximum flux that is generated in the chip. Is that clear?
Clear, sir.
I can better. I think it is clear. Should I draw the diagram again?
No need, sir.
This was air, and this was the chip, say temperature of chip, contact resistance, and circuit board, resistance of circuit board, and the convective resistance of air again. And in this case again, heat will be generated. It will go to top and bottom surfaces, and the equations will remain the same as previous. The only thing is that in this case the known value is temperature and unknown value is flux. That is the difference. Okay. There is some
Okay, sir.
yeah. The concept is clear, but as you indicated, there is some confusion with values, but that is the problem with the question. But in any case, the concept is clear, right?
Clear, sir.
Yeah. What about others? Is it clear for everyone?
Yes, sir.
Yeah. So we have looked at 5 questions today. Let me know. The moment that you
Sir, what is answer for? Sir, what is answer for B? Fifth B
let me check.
is 67.
It should be 67.16. Yeah. Are you getting that answer?
Yeah. Yes, sir.
Okay. Yeah. That is 67.16 kilowatt per meter square. Right. These 5 questions are what I had prepared for today. That will conclude today's problem solving session. And if the session is clear for you, you can leave the meeting, or if someone still has some confusions, I'll be happy to remain in the meeting and help you out. Should I go through different?
Thank you, sir.
Okay. Are all the 5 problems clear?
Clear, sir. Kindly share the PPT, sir. So it is very much helpful for us. Oh,
Okay,
through
okay.
proper chat.
Yeah, I will be uploading this presentation in a common folder, and I will be sharing the link to the course coordinator, and I think the course coordinator will share these links. I will ask them to share this link to the enrolled students.
Oh, thank you very much, sir.
Also,
Thank
I am actually recording this session, so this recording will also be available.
you. Oh, kind of you, sir.
Yeah. Thank you all for joining the session. Thank you very much. Are there any questions?
Excuse me, sir.
Yes.
Sir, in the fifth one.
Fifth one.
Yes, sir. Yeah, sir. I haven't seen the video set, so I'm not sure if my question is right. But in the answer that you wrote the equation, if you can, sir, why should it not be minus in between here?
Where?
Tc minus T infinity by 1 by h naught minus Tc minus in the middle.
No. See what is happening. The total heat. Okay. Total heat that is generated is Q. Heat flux generated is QC.
Yes.
This portion is at a higher temperature compared to this point. Say I'm calling it point 1, and I'm calling the bottom point 2, and the chip I'm calling point C. Point C, PC, is the source of heat. It is at a higher temperature. So heat is flowing from both PC to P1 and from PC to P2. Do you agree?
Yes, sir.
Do you agree?
Yes.
Yeah. So the total heat generated, that is QC, it is a combination, it is summation of heat that is flowing in these two different directions.
Yes.
Total heat generated, it is being dissipated from top and bottom, and if we add up those two quantities, we will get the total heat generated. That is why we are adding this heat this is the heat. The first part is the heat dissipated through the top part, and second part is the heat dissipated through the bottom. If we add that, we will get the total heat that was generated. Heat flux.
Oh, I see, sir. I see. I think okay.
It's clear, right?
Yes.
Okay.
Yes. Thank you, sir.
Yeah, thank you.
Thank you very much, sir.
Thank you. Any other queries? If there is no further queries, I think I will end the session here. Is that okay for everyone?
Okay, sir.
Yes, sir.
Okay. Thank you for joining.